Engineering being a inherently quantitative science really requires us to have a good grasp and handle on how we measure things and how we relate the mass of something to a mass unit that someone else understands. And so we're going to spend a little moment talking about units commonly used in engineering, some tips, tricks, and things to be aware of and things to avoid. Obviously, this is a very it can be a very dense and deep subject, one that you will continue to learn throughout your career. But here are some best practices to begin with. Most of science, engineering, and medicine generally use metric units. This is usually commonly found outside of the US in particular, and it's one that is a standardized set of units that is preferred by most professional science, engineering, and medicine societies for a very, very simple reason. One is that we can denote different scales of the same unit. So if we want to measure something like mass, we would use the unit of a gram, represented by a lowercase g. To represent a very large amount of mass, a heavy thing, many grams, we could easily write that as a kilogram, kg, which of course represents 1,000 grams. For a very small amount of mass, we could write a milligram, mg, micrograms, nanograms, and further on, representing different values or different scales of the same physical unit. This is quite convenient because we don't have to memorize a lot of different relationships. Most of these units are separated by a factor of 1,000. Uh, and it's quite easy to have memorized the relationship that a kilo something, in this case a kilogram, is 1,000 of that thing, 1,000 grams. A nanogram, lowercase n, is 1 billionth, or 10 to the minus 9 of that unit. A billion nanograms to 1 gram, or 1 billionth of a nanogram to 1 gram. Quite simple. Generally, we can apply these prefixes to really any of the metric units that we measure. Most of the common variables and physical quantities we deal with in engineering. We have a lot of different base units, including things like length, which we usually measure by the meter. And by using these metric prefixes, we can sort of build an intuition for the different length scales of the physical things we are likely to encounter. So it's helpful to understand and sort of have in your back pocket that the distance that sort of span across cities, so for example, the distance between my house and campus is in the range of 15 kilometers or 15,000 meters. We're able to use this kilo prefix to shorten and abbreviate these numbers. Both represent the same distance, of course, but one is more convenient and more concise to write. Things sort of on the human length scale is about a meter. That's one reason why we use a meter, because it's very relative and we can kind of easily grasp a meter based on sort of dimensions of our own body. And at the very, very small end of things down at the biological or nanoscopic length scale are down into the micrometers, sometimes abbreviated or referred to as micron. Again, as engineers, it behooves us, it's sort of a good trait for us to have a rough idea of the different length scales or the different orders of magnitude of these fundamental units. What does a kilometer look or feel like? What is a meter versus a nanometer or micrometer? One little note that may be necessary for some of us. Depending on where you were trained and grew up and you learned math, you may have learned different conventions, different rules for how we express very, very big and very, very small numbers. It's not quite a East versus West, North versus South, Europe versus South America type thing. It kind of is a little random. Here in this class, and particularly in the US, we use a notation that uses a comma to separate the thousand place. So if I wrote 10,000, the two standard ways I would write it would be 10 space 000 or 10 comma 000, representing a very large number, 10,000. And I will use a decimal point as a decimal separator Elsewhere in the world, they might use a comma for the decimal separator, but here in the US, we use this decimal point to denote things that are smaller than 1. So 1/10,000,000th, 0.000001, we represent with this punctuation and notation. So just one thing to put out there, it's it's hard to predict who follows what convention and inherently, but here in the US, this is the convention of writing our numbers. Now, within sort of the metric units, we have a lot that we will eventually become more familiar with, and we will start to remember and memorize most of these things. But in these early stages, and certainly for this class, you're more than welcome and encouraged to look up these things. Wikipedia usually has really good information and references for how we measure in the metric system. But we'll march through some that you are likely to encounter using metric units. If we measure length, we typically measure things in terms of meters. Again, they could be kilometers, centimeters, millimeters, but the base unit, the unmodified one, is a meter. When we measure mass, we usually use a gram. 1,000 kilograms is often seen as a metric ton, represented by a lowercase t as the abbreviation. Time, quite simply, we measure in seconds, and of course the corresponding minutes, hours, days, weeks, so on and so forth. Temperature, a particular note. In the metric unit, we often do use degrees Celsius, which is used far and wide outside the US. But for many scientific applications, particularly ones in chemistry and physics, we use this unit of Kelvin. Now, temperature, degrees Celsius, can be a negative number. On a very, very cold day, it could be negative 10 degrees Celsius, 10 below zero. But often in physics and chemistry equations, negative numbers break the equations. Negative numbers cannot be used in most calculations. And so we have this alternative scale called the Kelvin scale, which adjusts all the values to ensure that we have only positive temperatures. And we calculate the degrees, or we calculate the temperature in Kelvin by adding 273.15, this very specific number, to the degrees Celsius to get a temperature in Kelvin. Now, in addition to these base units, which are sort of the simplest physical quantities we might ever measure, there are many derived units that have special names, and we'll mention a few of them. When we measure volume, we might measure a dimension cubed, so meters cubed or cubic meters. And of course, commonly, when we measure fluids, you'll see liters as well as the associated milliliters with this millimetric prefix. If we talk about force, which is usually the amount of mass times acceleration, again, this concept from physics, we measure force in terms of newtons. Pressure, which is a force per area or force acting on a certain amount of area. Within metric units, we do have many different units of pressure. We might measure things in a Pascal, in an atmosphere. Bar, torr, and millimeters of mercury are all different units you're likely to encounter within your engineering career. There's different conversion factors between the different ones, and each one are more suited to different types of pressure, usually high, medium versus low pressure applications, and I'll leave that for you to explore on your own. If we talk about energy, so the amount of energy or work required to do something, within metric units, we measure things by joules is the standard unit. But because we live in an electrically powered world, you will often see things, energy or work measured in units of watt hours, which is watt times hour, so the power times the amount of time. And often our electricity prices, the cost of our energy that delivers electricity to our home, is measured in cents or dollars per kilowatt hour. And then finally, when we measure power, of course, this might be electrical power quite commonly, but also can represent any sort of power, whether it's a thermal power, sort of a steam engine driving things, or human power, ourselves pushing a block up a hill. We often measure in this unit of watt, represented by a capital W. Now, of course, because this is the US, we are quite unique in that we have not fully adopted the metric system. And most engineers, as well as many scientists and doctors, will tend to use a mixture of metric and so-called U.S. customary units. This is also true in Canada and in some aspects of Great Britain and Australia, but it does inherently complicate our work a little bit. And again, the reason why we typically don't uh, uh, or the reason why people typically don't use the U.S. customary units more often is because they don't quite have the same convenient prefixes associated with them. You may already be familiar that we have many different measurements of length, foot or inches, and they're not related by a convenient factor of 10. There are 12 inches per foot. You may also see, in the case of measuring very small things like the thickness of a glove, like a rubber glove, those are measured in units of mil, which is not millimeter, but representing 1,000th of an inch, 0.001 inches. Other customary units, of course, appear in mass, ounces and pounds, 16 ounces to 1 pound, 2,000 or 1,000 pounds to a short ton. And some applications you may see this weird unit of a hundredweight, which is abbreviated by CWT, which is simply 100 pounds worth of something. Luckily, everybody agrees that we measure time in units of seconds, minutes, hours, days, so on and so forth. But when we get to temperature, we have another set of adjusted units. Of course, here in the US, we commonly will measure things in terms of degrees Fahrenheit, but to solve the similar negative temperature problem as we had with degrees Celsius, engineering in particular uses this degrees Rankine notation, which is degrees Fahrenheit plus 459.67, again trying to get rid of any negative temperatures by sort of adding and shifting all the values up. Finally, once again, we have derived units. Volume, we have many different volume units. Do note here that within the US customary units, measuring something in fluid ounces is different than measuring ounces of something. One is a volume, one is a mass. They have different meanings to them. When we measure force, instead of measuring newtons, engineers here in the US will often measure pound forces, which is again different than the mass pound, represented by lbf. And then pressure, of course, has its own set of units here in the US. You will commonly see in gas cylinders for high pressurized things, the pressure of the air in your tires and in your car are measured in pounds per square inch, PSI. You may also see in many applications, and in many cases, people actually are referring to PSI gauge, which is abbreviated PSIG if people are very scrupulous. This indicates the pressure above the ambient atmosphere. So when you have your car tire that is at 40 psi, or let's say 30 psi, 30 pounds per square inch, in most cases that is 30 psig. It means 30 psi above the ambient pressure in the air, which for sea level is 14.7 psi. Things that you don't necessarily need to measure, but you'll tend to learn them as you go along. And then finally, energy within the US customary units has its own set of notations as well. You'll see pound feet or pound foot, which quite intuitively measures the amount of energy required to move a pound of weight 1 foot in distance. Oftentimes in heating applications or power generation applications, you'll see things measured in BTU, British Thermal Unit. Often on our air conditioners, their output and their cooling and heating power is measured in BTU. And then finally, one thing that you quite often, of course, you see in food applications in nutrition is a unit of a calorie, CAL. One important note is that the calorie that is labeled on our food, which is technically a capital CAL, is actually 1 kilocal, 1,000 of the sort of little calories, which is an important thing to make note of. And then finally, in power, we do quite often, again, we use mixed units as engineers quite often. We will use watts, which is a metric unit, but quite often, of course, particularly on things like the motor of an engine, you'll see the power measured in horsepower, which is an actual unit that is not directly related, that is not directly equivalent to the power of a horse, quite confusingly. One final thing that I want to touch on when we talk about units and measurements is that you'll often encounter what we call nominal measurements. Uh, you quite often see this in building materials, things in which you're measuring the dimensions, the length, height, volume, whatever it is of a piece of construction equipment or material. This nominal, when we say nominal, that means in name only, meaning that the name of something might be a measurement, but is not actually referred to the actual dimensions of that object. For example, if you were to go to Home Depot and you're to buy some lumber, you'd likely pick up a piece of 2x4. Now, the nominal name of 2x4 nominally refers to a height and width of 2 inches by 4 inches, and that is the approximate dimensions of a piece of 2x4 lumber. But the actual dimensions, if you were to measure it with a ruler or a tape measure, is closer to 1.5 by 3.5 inches. And because this is a nominal measurement and standards keep changing throughout history, you'll actually see in this picture that the actual dimensions of a so-called piece of 2x4 have been shrinking over the decades and over the years for a variety of reasons that we can talk about in another discussion. Another example of nominal measurements you'll see, again, you often see this in U.S. construction materials. You'll see things like PVC piping used for water makes use of this nominal dimension. You can see in these cross sections of various plumbing pipes that the nominal name, such as here in the top left, you see a 1/2 inch standard. Half inch refers to a nominal measurement, a nominal value, and this pipe is approximately 1/2 inch. But looking at the actual dimensions, you'll see that both the outer diameter, so the outer surface of the pipe, as well as the inner diameter are both larger than 1/2 inch, 0.84 inches and 0.622 inches. So it's definitely something to be aware of, that when something lists a measurement, we have to check that it is a real measurement, an actual measurement, and not a nominal measurement, not just the name of this particular material or piece of equipment.